we're going to talk about decision trees for machine learning. It's a very popular supervised learning technique. This comes to you through my YouTube channel AINEXUS and the playlist Course on ML. I'm Dr. TV Geeta. Please subscribe to this channel. Now, what are the learning objectives of this video? To define a decision tree and explains its role in supervised learning. Explain how a decision tree learns by recursively splitting data. Understand node purity and what makes a good split. Explaining and understanding entropy, information gain, and Gini impurity. How decision trees can be used for both classification and regression. How to understand overfitting and controlling of tree complexity, and then identify the major disadvantages, limitations, and real-world applications of decision trees. So first, let us understand what a decision tree is. Decision tree is actually learning by asking questions like, is the weather sunny? Yes or no, like that. So it's a supervised learning. It can be used for both classification and regression, and it's very easy to understand. So ask, split, decide, and then predict. So why decision trees? Because simple questions can lead to smart decisions. So easy to understand, easy to visualize, requires little pre-processing, handles non-linear relationship, produces interpretable results, and useful for both classification and regression. So anatomy of a decision tree, root node, for example, the starting point here is the weather. Sunny is an example of root node. Internal node represents the decision or a question based on feature. For example, here is the humidity high and is it windy are both internal nodes. Branch is where you ask the question and I can come to yes or no. And then the end node or the leaf node, the final output of prediction, because we are not going to split it further. So in this example, play tennis, the tree asks questions, follows answers, the branches, and reaches a decision, the leaf nodes. Now, how does the decision tree learn? It is a step-by-step learning process. You start with the data, the complete data set, examine the features, look at all the features and possible split points, find the best split, choose a split that makes the data purer. We will explain this as we go along. And then you divide the data into smaller groups based on the split. You repeat this recursively for each subset, and the stop condition is stop when either you've got a pure node or the result, or you have reached a maximum depth or minimum samples as specified by you. Assign prediction, assign a class label for each leaf node. So this is how the decision tree learns. Now, decision trees, what makes a good split? Because the whole thing depends on the splitting. So a good split creates purer groups. It reduces uncertainty and increases information so the tree can make better decisions. We'll go into detail later. So for example, you have before split, so 100 samples, you have 50 cats and 50 dogs. So you can split on pet type. So here you have 45 cats and 5 dogs, which is a high purity, and 45 dogs and 5 cats, also high purity. So easy to understand, easy to visualize, it requires little pre-processing, and the rest of it which we have told, and the results are interpretable. Okay, a good split in this case creates purer groups, reduces uncertainty, improves prediction, and leads to a more accurate tree. Now we're going to go into that. So first we have to understand how entropy measures uncertainty. So what is entropy? Entropy measures the impurity of uncertainty in a set of data. Lower entropy means more purity and less uncertainty. So the formula for entropy is equal to minus summation of 1 to C pi log to pi, where pi is a proportion of class I and C is equal to number of classes. So in binary classification, pure node means all the nodes belong to the one class. There is no uncertainty. mixed nodes, some samples are there from each class. Example 75% green and 25% orange. The entropy here works out to be 0.81 after applying, approximately after applying the formula. And maximum uncertainty is when you split and you get equal number of classes. So that is the maximum uncertainty. So entropy range, as you've seen, is between 0 and 1. And if it is 0, it is completely pure. It is 1, it is completely uncertain. So it helps to decide the best split. A good split will reduce the entropy and create purer groups. So entropy versus class distribution is given by this graph. Now, how do we do this? So information gain can be used to measure the value of a split. So what is information gain? Information gain, or IG as it is called, tells us how much uncertainty entropy is reduced after a split. So higher IG means better split. So information gain is equal to entropy of parent minus weighted entropy of the children. You do this by splitting differently and find out which gives the most information gain. So before split, the parent node is like this. After split, it will be like this. So here entropy of parent is 0.97. That is where we've used the previous slide formula. How it works? So after split, you have Sunny and these three. So Sunny 30s 10, no? So the entropy is 0.81, overcast and so on. You get this. So the calculated weighted entropy of child nodes is equal to 40 by 100 into 0.81 plus 30 by 100 into 0.65 and 30 by 100 into 0.65. These are got from here. So that is equal to 0.324 plus 0.195 plus 0.195. That is 0.714. So the information gain is the entropy of the parent, which is 0.97, minus the calculated weighted entropy of the children, which is minus 714. So you get here as 0.256. So it finds the most informative split that will lead to pure leaves and improves accuracy of the tree. And information gain is to do about reducing uncertainty and make better decisions. Information gain is not the only method. There is another one called Gini impurity. So Gini impurity measures how mixed the classes are in a node. It is 0 for a pure node and highest when the classes are evenly mixed. So all the Gini impurity formula is given here. 1 minus I is equal to 1 to C. C is the number of classes, Pi squared, where Pi is the proportion of class I. So all samples belong to one class means Gino is equal to 0. There is no impurity. Mixed means Pi is 0.6 and 0.4. So the Gini impurity is 1 minus 0.6 the whole square plus 0.4 the whole square, which is 0.48. So there is some impurity. And equal number of classes, you get it as maximum impurity. So good split reduces Gini impurity in the child nodes and create nodes with purer than the parent classes. So it varies from 0, which is pure, to maximum impurity 0.5. So between 0 and 0.5, you have some impurity. So it helps the Gini impurity helps decision trees to find the splits. Okay. Now let's compare entropy versus Gini impurity. So already we've seen higher classes, higher when classes are more mixed. So entropy, we've seen the formula already. So measures uncertainty, that is entropy. Gini impurity measures mixedness. So for example, for impurity for binary classification, entropy 0.1 is maximum, Gini 0.5 is the maximum. Both are 0 when the node is pure. And then meaning, it measures uncertainty, it measures mixedness, the aspect. And the formulas given here, and range 0 to log 2c and 0 to 1. Sensitivity, it's more sensitive to small changes in probabilities, entropy, but less sensitive, Gini impurity. Computation slightly slower because you have to take log for entropy. Faster and simpler, no log involved. Used in practice, there are a lot of algorithms available for decision trees. So ID3 and C4.5 are typical algorithms available for decision tree. That is uses entropy. But CART, which is the most widely used, uses Gini impurity. So both measures help find the best split. Gini is more efficient. Both lead to great trees. Next, can you use decision trees for classification? Predict the class label? Yes, it can. So if you are given, this is a famous example that is available for decision trees, that is play tennis. So you have outlook. So you find out it can have values of sunny, overcast and rainy. So it's a three-way split. So is it sunny? Is it overcast? It is rainy. Now if it is overcast, okay, then you play tennis. Okay. Now you have to check the humidity. Now humidity is high because there is only one value for overcast. If humidity is high, if it's sunny and the humidity is high, then you play. If it is normal, I mean you don't play. If it is normal, you play. And then windy, so you come down. So if it is strong, play. If it is weak, don't play. I mean, if it is strong, you play. If it's weak, don't play. So here we have written it as rainy. Actually, it is windy. And the result classifies new examples as play, yes or no, by going through the tree. So root node, all the data will be at the start. Decision, you will test a feature. Rainy, and then you check the wind, which is weak or strong, and so on you go. Strong actually value is not, it's not if it's weak, and so on. So you just check out this, you will find out how to draw that. And interpretable rules handles both numerical and categorical data, works well for prediction problems. Now you take decision trees for regression. You start at the root node, split the data based on a feature and a threshold that reduces error. So at the then repeat on each child node. At the leaf, predict the average, largest value of training samples in that leaf. So let's take the example here. So house size, if it is, we are taking that value, okay, less than or equal to 1200 and less than or equal greater than 1200. Then so here we have two values which are greater and three values which are lesser. So now you check out the location. So if the location is good, okay, then the price location is good. So less and location is good, your price is 40 lakhs, and if it is average, your price is 25 lakhs. You have to calculate that. We'll see, come to that later. If it's greater and the location is good, then you have a price of approximately and the bedrooms, it depends on the bedrooms also. Bedrooms is lesser than 3, then 55. If it is greater than 3, it is 70. Similarly here also it's like that. So here predicted numerical value, average of training samples in that region. That's how we give this value. Internal node splits on features with threshold. So this threshold has to be decided. Leaf nodes outputs a numerical value, average prediction, uses metrics like MSE, mean squared error. Choose the split that minimizes the error within the child nodes, okay, and captures non-linear relationship and easy to understand and interpret. Now overfitting in decision trees, can that happen? Yes. Overfitting occurs when a decision tree learns the training data too well, including noise and outliers, and fails to generalize on new data. So the same that we have seen before also. Good fit, it should be balanced. It should calculate the main patterns but generalized unseen data also. Overfitted, it's a complex tree, so the noise and outliers, everything is learned. And underfitted, it's a shallow tree, so too simple to capture the patterns. High bias, here you have similarly whatever we have defined in the previous slides. So how to prevent this? Prune the tree, remove branches that add little value, limit the tree depth, restrict the maximum depth of the tree, increase minimum samples per leaf. So require more data if you want to make a split. Use more data, add more training data so that you can improve the generalization, and also use cross validation. Now you want to control the tree complexity, then how to do that? Controlling the tree complexity helps prevent overfitting, improves generalization, and builds models that perform well on unseen data, which is what we want. So limit maximum depth. Okay, minimum samples you require if you want to split. Minimum samples should be in the leaf node. Minimum impurity, that has to decrease if you want to do the split, and use pruning. So example data set could be like this. It could be used in a number of places like customer churn detection, which we will see later. Okay. The advantages of this particular decision trees are easy to understand and interpret, requires little data preparation, handles nonlinear representation also, the complex pattern. Feature importance you can provide. Which features actually are more important in this particular, in the data set. And works for both classification and regression. Limitations are it's prone to overfitting. There is high variance. Small changes in data can result in a very different tree. Bias towards features with many levels, may prefer features with more unique values even if they are not informative. Piecewise constant predictions. Changes in prediction occur in steps, not smoothly. Applications include customer churn prediction, medical diagnosis, credit scoring, recommendation systems, agriculture crop yield predictions, fraud detections. So with this, let's look at the summary. So decisions are, as we told, supervised learning algorithm. It can be used for both classification and regression. You use the trees repeatedly. You start with the whole data set and you split repeatedly into smaller groups. And the good split generally produces more homogeneous cluster group or pure group. Entropy measures uncertainty, while information gain measures the reduction in uncertainty, and Gini impurity generally indicates greater purity. Complexity can be controlled by uh, limiting the maximum depth, splitting only if you have minimum samples, and so on. Their major weaknesses include overfitting, instability, and reduced interpretability for very large trees. So these are the references both offline and online. These are short answer questions and questions. I've given a number of problems here so that you can understand how entropy, information gain, Gini impurity, best split, prediction, regression tree, tree interpretation, model evaluation. Model evaluation we have not covered here, but we have already covered that when we are talking about model evaluation video. So please go look at that. So with this, we'll conclude. And then we have the problems. Then we have mini projects. So here again, it gives you a feel of decision trees. We have given you 3 mini projects. So thank you. Please do subscribe to my AINEXUS channel, especially the playlist on machine learning. And the next video, we're going to talk about an ensemble learning method called random forest. So that's what we're going to cover next. Thank you.